So this isn't going to be as fancy as what Rob Skibba did, but I think simpler is better sometimes, and I'm just going to try to explain the exact science of what I understand is going on between flat earthers and globalists, as they like to call us. So here's a quick introduction into atmospheric refraction and why Rob Skibba's last video is scientifically inaccurate. So, first thing I'll do is show you some slides to get you through the theory, and then we'll go to a practical demonstration. So, the first slide I want to show you is a slide about basic intro to lenses and refraction. So, focus on the top left. We have a basic prism. Kind of looks like a triangle. You might have seen it before. But the important thing to notice about how a prism works is that when a light ray goes in, so from the left to the right, it's going into the prism, it is going to bend toward the thicker side. And without going into all the math behind it, the way I like to think about it is if the beam had a little bit of width, or like say it was three guys with their arms locked, and they ran into this barrier, well, obviously the guy on the right side going into it is going to have a harder time getting through than the guy on the left side because he has less to get through. So it's going to be quicker for him to go through the beam than the guy on the right. So if you want to think about it this way, you have this beam of light coming through, and the right side of the beam gets slowed down as it tries to get through more and more material until it passes out on the other side and can go straight through. So that's why prisms bend light. If it were the same thickness, it would go straight through. But instead, it's a little thicker on the right side, so the light gets slowed down on the right side, and when it emerges, it's heading down. That's called refraction. So the two types of lenses you can have based on that are obviously a concave lens, so it's two prisms where the thin points touch. And what happens is light comes in, the light on the outsides gets bent toward the thicker sides or away. And the light in the middle obviously passes straight through. So that's going to be called a divergent lens or a concave lens or a negative lens. And that is going to make whatever image is on this side blow up and get bigger and bigger on this side. On the other side, the only other lens you can have is a convex lens. And that is two prisms where the thicker parts are in the middle toward each other. So what happens in this case is when light's going straight into the lens, the light is going to get bent toward the thicker side on the outsides, and all the light is going to converge toward a focal point. So that means all the light coming in parallel rays on this side will all meet together at this one little tiny point and then continue on their ways. So this bottom ray will start out on the bottom and then start going up on the other side. What this effectively means is that light gets flipped, or you see a mirage image. So if we were to see a stick figure on this side, let me draw one. Before, at the focal point, if we were to observe it, we would see the same stick figure, but a little smaller because the light rays get squished. And on the other side of the focal point, we would see the stick figure flipped because the light from the top has now gone to the bottom and the light from the bottom has gone to the top, effectively flipping the images. So those are how the two major lenses work. This would be a normal convex lens, drawn up a little bit bigger. Again, it's still convex even though one side is flat because the middle is thicker and the outsides are thinner, and it still converges to a focal point. And the reason I show you this diagram is to show you what a Fresnel lens looks like. And basically these two lenses do the exact same identical thing, only here you have a very thin lens versus a very thin lens. And that is because the way this lens is cut it is still going to bend light in approximately the same way that a thicker lens would, based on the curvature of these smaller segments in relation to this middle segment. So that's why I've gone out and I bought the same kind of lens that Rob Skibba used. Here you can read, it is a 2x power acrylic Fresnel lens. So that's essentially what it is. It's a flat sheet made out of glass, and I'll show it to you real quick. And here you go. Here's the Fresnel lens. So you can see it's doing some weird light magnification things behind it, but I've drawn some little dashes on it to show you where the center of the lens is and how it radiates as a circle around, and the crosshairs to show you where up and down and left and right are. So we'll get back to that more in a second, but I wanted to show you that real quick because that's the same kind of lens Rob Skibba uses in his experiments. So now that we know the basics of how lenses work and how light moves through those lenses, the next thing we need to talk about is a little bit of atmospheric refraction. So here, if we focus on the left, this is a plot of density versus altitude. And this is backed up by tons of experimental data. You can go out and find it online, but basically know that on the bottom axis, so this horizontal one, this is 0 feet, or basically at sea level, which is what altitude is defined from. And as we go this way, we get closer and closer to space. This vertical axis is our density of the air. So here you can see that we have maximum density at 0 altitude. So that's this line right here. Basically, at the top of this line, our density is really, really high, corresponding to this axis, but it's at a very low altitude, or sea level. And then as you go up in altitude towards space, the density decreases. And what that ends up looking like is this picture, where here's our surface. So it doesn't matter whether it's a flat earth or a curved surface. This is our surface as it would be seen by us. And these dashed lines represents different layers of the air as you go up. So obviously the stick figure in this layer is in the thickest part of the atmosphere. The next layer is less dense, the next layer is less dense, and the next layer is less dense. And what you can think of that is different prisms. So basically this is the thick part of the prism, and this is the thin part of the prism. So these first two layers form a prism. These next two layers, you can also think of that. It's a little bit thicker than the layer above it, and so it forms a prism. And so what that happens is, if you're looking at the sun, essentially the sun may be here in its absolute position, but as the light passes through these layers of atmosphere, it gets bent toward the thicker layer, and then bent toward actually where it actually hits your eyeball. But all your eyeball knows is that the angle that this last little light ray hit after coming through this last layer is where the sun looks like. So even though the sun's closer to the horizon, it looks like it's further in the sky. And that actually makes sense because lenses don't have any discontinuities or jumps. They basically will take your image and spread it out or shrink it down. And in this case, it's going to spread the image out. So if you think about it, if the sun were completely vertical, coming straight down to you, it would look like it was straight vertically above you. And it's not really bending left or right because it's hitting these layers straight on. And then as it moves over a little bit, it's going to still look like it's closer to the center until it's all the way down toward the horizon, where it starts to go below the horizon, and then light is bent around until it exceeds you, until the sun is so low that the atmosphere can no longer bend the light quickly enough to actually get to your eyes, at which the sun vanishes right beyond the horizon. So just a reminder, light bends toward the thick side, which is why this principle works. The other thing I want to point out here is that in this scenario, though, your thickest layer is where you are at the surface. So if we're relating that back to this little convex lens, like on this page, and the Fresnel lens that we're actually using, the thickest part is exactly in the middle of the lens, which would correspond with sea level. If you go any lower on the lens, you start to get to thinner and thinner layers, which doesn't exist in reality. The thickest part of the atmosphere is at sea level, because that's just basic physics. Gravity pulls all the air down to the surface, and the air cannot go below water or earth because it is not as dense as water or earth. So really, in these experiments, we should only be using the top part of the lens. Which leads us to our last slide before we get to the cool stuff, and that is Rob Skibba's big mistakes. So we'll focus on mistake number 1. Early in his video, he theorizes that there are a bunch of tiny little water droplets in the atmosphere, and that somehow when they are all together in the atmosphere, they form one giant lens that you see the atmosphere through. And that's absolutely false. If the air were composed of uniform water drops, light would uniformly scatter through it, and it would look a lot like looking through glass. Exactly. There wouldn't be a lot of distortion. The light would pass through relatively straight. You wouldn't see this prism effect, or the bending of light that you do get from these layer model of the atmosphere. So that's his false assumption, number 1, that he makes a mistake on. Number 2, the weatherman's lens placement. If you go back and look at the video that he posted, the weatherman has the lens on the opposite side of the table, in between the picture and the viewer, and the table. And if you notice his lens placement, it's exactly halfway covering the lens, which goes back to my statement about how we're only using the top half of the lens according to our atmospheric model, because the thickest part of the atmosphere is right where we are. So this is in contrast to Rob's placement, where he clearly has a majority of the lens above the table, which means he can view through his camera lens below the center of the lens, which is going to cause the light to refract in the wrong way. And we'll show that in a little bit. His last mistake is very similar to the number 2 mistake. Number 2 is more about not replicating the experiment faithfully to how the weatherman presented it. The last one is more closely related to the camera's placement. And as I said before, he places the camera below the midpoint of the Fresnel lens. So, real quick, if we show it with our Fresnel lens, here's my little axis. He's placing the camera below, and you're only seeing the effects of the bottom half of the Fresnel lens instead of the top, which is what is more physically accurate, what's going on in the atmosphere. So with all that said, let's just go do the experiment now. So if we come in here, I have a little box set up on my bed that happened to be the perfect height to see only the top half of the Fresnel lens. So now if I set my camera down and we'll look toward the further end of the range, I can get it to stay. The first thing I want to show you is the effect that this has on a distant object. So if we remove atmospheric lensing, which I'm going to do by just pulling the Fresnel lens down, which causes everything to fall. Sorry. Again, this is not as smooth as this video may be. You can see my little book off my little bookcase or collection of books off in the distance. Orson Scott Card's a great Arthur. You should read some of his books. Anyway, so we pull the lens back up, and you can see how much bigger that book tower is. And again, remember that this is a circular Fresnel lens. So what you'd really see in the atmosphere is a flat Fresnel lens with thicker layers on bottom all the way across. But because we have a circular one, the sides get distorted too. So not only is it bigger in width, here you can see it's about this big. When I put the lens down, it's much smaller, but it's also a lot taller. And so that's just an artifact of the scale of the lens we're using. If I need to, I'll make a better video later using the proper lens to show that effect. Now, the big thing I want to show is Rob Skibba's attempt to explain how a flat Earth sun appears to go below the horizon. And right now, if we move this little smiley face back, which is my sun, again, you can see I'm moving it flat on the ground. It actually goes up into the atmosphere, not down as we saw in his last video. And that is exactly because we're viewing the lens from the midway up, which is more physically accurate than his method. So that was his flat Earth sun moving flat with the Earth. If I were to do a demonstration with my globe or my sun, what we'll see is that there's not much difference in this sunrise to what you actually see happen in real life. Granted, the scales are not accurate, so my sun would look a little bit bigger than it would directly overhead because of the distance involved. This is like, 3 feet, whereas in real life the sun's 93 million miles away. But with all of that said and done, now I want to show you how I can exactly replicate Rob Skibba's results, which are physically inaccurate, by putting my camera now below the point. So there's the crosshair, right? You can see that bottom line. Now we're below the midpoint of the Fresnel glass. And if I put my little Rob Skibba sunny face right up to the video, we can watch as it now seems to go smaller and smaller and eventually set below the camera. Well, I need a little bit more height on this to show you that, because we're still close to the center of the Fresnel lens. Yep, see? And he's disappearing. So that, in effect, is the disingenuine nature of Rob Skibba's science that he showed you. He did not fully understand how the atmosphere works as a lens, and did not understand how that refraction would play into celestial objects orbiting either on a flat plane or, as we globalists believe, around the sun. So if you wanted to learn more about this video, I hope that was educational. If there's anything I can do better about this video, please let me know. And hopefully we can all find some common ground. Because I honestly like flat Earth ideology. It's like science fiction almost. I enjoy delving into it and figuring out how it could work. But at the end of the day, the more repeatable and predictable experiment lends more credits to what I actually believe is physically out there. And while I have never been off the face of the Earth, trust me, one day I will be an astronaut, and I am going to places like Mars and Venus, and I will explore our solar system. Until then, I'll just have to keep using basic scientific principles to prove what's really out there. And hopefully you guys do the same. So, alright, thank you. Have a good day. Bye.